All right, let's talk about the exam problem number 6. Talking to people, many people told me that they felt pretty good about problems 1 through 5, and then they were a little bit unhappy about problem number 6. Said that it was confusing, they weren't really sure how to approach it. So I want to go through how I approached it, and then hopefully that'll help you when you see problems like this one in the future. So this one was a little bit different than some of the things that we've seen before in that we didn't have a molecular formula. Right? Like some of the problems we had seen, we had a molecular mass, not a molecular formula. So it was a little bit harder to figure out how to get started. So we had to just figure out what could be here based on the spectra and then see if we could construct a molecular formula from that. So the key IR peaks, 2950 and 1740, right? And what does that tell us? Well, hopefully this tells us that we have an ester. Right, and then that tells us we have CsP3 to H. Right, so it doesn't look like there are any carbon-carbon double bonds. Doesn't look like there's any CsP2 to H, so we probably don't have a benzene ring or any alkenes. But we do have an ester. Right, and so then if we jump to the carbon-13 NMR, it's sort of interesting. In the region where we expect the ester carbonyl to appear, right? And again, hopefully we're thinking about our ester functional group, right? We would expect that peak to be, I don't know, somewhere around 170 in the carbon-13. We note that we have 2 peaks in that region in the carbon-13 NMR, right? And that's a little bit weird for us, right? But what we should conclude is that this means we have 2 esters. Right, that's a critical thing for us to conclude based on that. Right, so we have 2 esters. Right, so we should be thinking that we have two of those functional groups in our molecule, and that was a critical finding. Right, if we recognize that, we're able to do this without incredible amounts of difficulty. But if we don't recognize we have 2 esters, this problem becomes essentially impossible. Right? So that's important. Those 2 peaks are carbons attached to oxygen, which makes sense because we have 2 carbons attached to oxygen. So that makes perfect sense. Right? If we add up the peaks, we have 6 carbons. Right? So 6 total carbons. Right? So we might be thinking C6, 2 esters, O4. Right? That's starting to get towards a molecular formula. If we look at the Proton Nmr, we have the integration ratio over here. If we divide by 26, right, we figure out that this is 1 to 3 to 3 to 3. So that's 10 hydrogens. Right? So based on 6 total carbons, 2 esters, which is 4 oxygens, and then 10 hydrogens, we could guess that we have C6H10O4. If you do the math, that equals 146 grams per mole. All right, so that was very helpful figuring out that the molecular formula is C6H10O4. All right, that was very helpful. So now we can proceed knowing that we have all the carbons in our molecule. If we think about what's going on here, this is going to be a CH, CH3, CH3, CH3. Now we just have to start putting fragments together. Okay? Hopefully it's clear this is an O to CH, and that's an O to CH3. Right? And so that starts to help with what we're doing with our esters. Right? So if we're thinking about what's going on with the esters, all right, we have one of these O's attached to a CH, right, and then the other one, we have the O attached to CH3. Okay, and then we just need to figure out, you know, what happens over here, what happens over there. Okay. If we start to look at the multiplicity, right, we can see that this CH is next to a CH3, right? And here's the CH3 that's next to that CH. So that must be OCH, right? So we can see that this CH is now attached to a CH3, right? And that's got to be connected to something else over there. This CH3 is a singlet at 2.2, and that tells us that this is next to a carbonyl, right? So with all of that information, we can start drawing out some structures. And I think that we've got things reasonably well figured out, right? So based on what we just said, I think we can say we have a CH3 there, CH attached to CH3, and then the CH is attached to the carbonyl, and then that's attached to OCH3. And I forgot an oxygen, right? So this is really important to do, because this often happens, right? So I did this whole thing out, and I only have O3, right? So I forgot an oxygen right there. And this often happens when you're doing these problems out. You write it out, and then something doesn't look right. So let me write this again so I can actually get the correct molecular formula. All right, there's my ester. Now I have the CH connected to the CH3. Connected to the ketone, or the carbonyl of the ester. All right, so this has 1, 2, 3, 4, 5, 6 carbons, C6, H, 3, 6, 9, 10, O, 1, 2, 3, 4. All right, so we have the correct molecular formula. And if we just want to verify, so again, that one was wrong. If we want to verify this, we can look to the carbon NMR. So one of these is going to be 175, the other 172. This one, carbon, is probably going to be 64. This one will be 55. And then, 21 and 18, it doesn't really matter. You can interchange those. And if we look at the proton NMR, we can label everything out. So this is going to be 5.2. The quartet for 1H, and it's at 5.2. It's alpha to a carbonyl and next to an oxygen. The singlet at 3.8 for 3H, right? The OCH3, 2.2 singlet alpha to the carbonyl, and then 1.5 doublet for 3H, the final CH3. All right, so all of that works out, right? And again, the key here was recognizing that we had two esters from the carbon-13 NMR. That was the critical point. And then trying to build the molecular formula so that we could figure out what pieces we had and what the molecular formula was. All right. So again, definitely a challenging problem, and recognizing those two esters was the critical point.